Let's try again. Perfect. All right, so I'm Marco Gabuardi, and I will present this joint work with Romain Péchou about algebra and coalgebra in the light affine lambda calculus. So let me give you a very brief introduction to the research area where this work originates from. So you are all familiar with a very classical result about computability theory, that we can design programming languages that correspond to Turing machine. And an example is the lambda calculus or other languages. Maybe you are a bit less familiar with the fact that we can do the same also for complexity classes. People have designed different programming languages that correspond to the different complexity classes that we can identify on Turing machine. And indeed, this is the area of implicit complexity that aims at designing these languages. And this is the context of my talk. And today I will focus in particular on one of these languages, the light affine lambda calculus, which correspond to the class p-time. So you may wonder why people try to design programming languages corresponding to complexity classes. A theoretical answer can be because we want to understand complexity class better, but I believe we can also learn something more practical from this. In particular, we can use ideas from this research area for design resource analysis, for design more efficient implementation of, for instance, arithmetic operation, and also to model adversary in security model, where, for instance, we require an attacker to be modeled by a program working in polynomial time. But let's go back to the language that I will consider today. I say that it corresponds to the class p-time, but let me be a bit more specific. What is this correspondence? So we have that every program of this language can be run in polynomial time, and this is the soundness. And we also have a completeness that says that every p-time Turing machine can be expressed in the language. Now, if we look at the completeness, this is not what we would like, because it goes through an encoding of Turing machine. And this is something that doesn't tell us anything about the expressivity of the language, about the kind of programming primitives we have in the language for writing our programs. And this is the kind of question our work tried to address. Several people have tried to understand the expressivity problem in languages coming from complexity classes. And we address today the question whether we can encode in this language algebras and coalgebras or not. The reason for asking this question are two. Algebras and coalgebra are a natural way to define inductive and co-inductive data types. So if we can encode them in the language, we can encode them in data types, inductive and co-inductive. And the second reason is that the language that I'm considering is a subsystem of system F, where we know that we can encode some form of algebras and coalgebra. So if we succeed in encoding algebras and coalgebra in this language, we also know that we can encode them in several subsystems of system F. And here our result. So we show that we can encode the restricted notion of algebra and coalgebra in this language. But this restricted notion is not what we get in system F. And in particular, while we can define naturally inductive types, we cannot define interesting co-inductive types. So as a third step, we show how to relax the restriction of this language in such a way that we can achieve more expressivity, and we can now have co-inductive types. Okay, after this sneak preview, let me go a bit more in the detail after a glass of water. All right. So I want to give you the intuition behind this language. I will not present you the all detail, but let me say something. So, as I said before, this is a subsystem of system F, and in particular is a subsystem of a linear, or better, affine version of system F. And the main idea is the one of refining the function space of system F in two other function space. The first one is the one of non-iterative functions, linear function that use, or better, affine function that use their argument at most once. The second one is the one of iterative functions, so function that can iterate. And here we denote this function space with these two modalities, bang on the input and paragraph on the output. Bang is a marker of duplication, that we need to perform a duplication, while this paragraph is a placeholder witnessing an iteration. Let me give you an idea why this limits the computational power of system F. If we consider iterator in this language, they have this type, iterators like church numeral. If you strip the modalities, you will see the type of system F church numerals. Now, if we try to apply this iterator to a linear function, everything goes well. We can iterate a linear function as much as we want. If instead we try to iterate an iterative function, you can see that we have a type mismatch, because we need a uniform type A, but instead we have these two different types, bang A and paragraph A. And so we limit the computational power of the calculus to be polynomial. Obviously, there is a proof for the polynomial soundness, but I will avoid it here. And instead, I will focus on the question of whether we can encode algebras and coalgebra in this language. Let me give you a brief reminder of what algebras and coalgebras are. So an algebra for a functor f is an object A and the morphism from f of A to A, while a coalgebra is an object B and the morphism from B to f of B. For my talk, it's interesting also to look at a particular class of algebras that are the weakly initial algebras. These are algebras that I denote with this notation mu x f of x. And they have the property that for every other algebra A, we have an homomorphism H from the initial algebra to this other algebra A. If you are familiar with the more popular notion of initial algebra without the weakly, these also require a unique property of the homomorphism, while here we are relaxing this uniqueness. And we have a similar notion for coalgebras, where we have a weakly final coalgebra that I denote by this notation nu x f of x. And I require now the existence of an homomorphism from every other coalgebra to this coalgebra. Okay, why these are interesting? Because, as I said before, we can encode the standard data type, inductive and co-inductive, with this notion of weakly initial algebra and weakly final coalgebra. For instance, we can encode natural number, list, and trees in the inductive version, and the infinite analogous in the co-inductive version. Okay, so why I focus on the notion of weakly initial and weakly final coalgebra? Because it is a well-established result that in system F, this is what we can encode. So if I refine our research question is, can we give the same definition in this other language, the light affine lambda calculus? To answer this question, a natural way is to look at an encoding that give the theorem that I stated in the slide. And I will take the encoding given by Wright and Wadler that I report here. So this encoding uses two ideas. use polymorphism, and in particular, in the case of the initial algebra, I have a polymorphism algebra, a polymorphic algebra, and in the case of coalgebra, I have a polymorphic coalgebra, and also use the idea of continuation. Here is the encoding. I don't want to go through all of it, but let me try to observe a few things. The first one is that to build the homomorphism, this encoding uses the algebra towards which we want to build the homomorphism. In particular, this algebra morphism F. The second observation is that if we look at the term that defines this encoding, we have that the continuation is duplicated. Because algebras, initial algebra, represent some form of iteration. And so here we have an iteration. So to look if we can do this in our language, we have to try to use the iterative types. So we can add this bang and paragraph everywhere. And this gives us a diagram like the one I pictured here, which is a bit unsatisfactory, because now, if you look at the bottom line, I don't have the algebra morphism F I had before. But we can do a further step, and we can refine this diagram and recover this F with the condition that we add a left distributivity of the paragraph on the functor. So this is the restricted notion of algebra that we can achieve in this language. We require that we have this left distributivity for the functor. We can do something similar for coalgebras, and now what we need is a right distributivity. So these two notions are like the usual weakly initial and weakly final notion, but we have these two distributivities. So to understand the expressivity of this encoding, we need to look at this distributivity. And if we look at the left distributivity that requires to take out this paragraph from a functor, this works great, because we can do it for all the examples we want. So in particular, this means that we have all the inductive types we usually want. But the bad news is that if we look at the right distributivity, these fail everywhere. So in particular, we cannot push this paragraph inside. And this is the problem, that the modality paragraph does not commute with the other type constructor. Now, there is a natural solution. When we don't have it, we can just force it. So we can, in particular, make it happen. And to do this, we can add some primitive that perform this distributivity. But this primitive has some computational content. And in particular, they change the properties of the reduction. And in particular, they break the proof of polytime soundness. But this is not too bad, because we can recover it with a new proof that I will not present to you, but you can find it in the paper. So what we achieve once we have this distributivity is that now if we look again at the functor I presented before, that remember are for the co-inductive version of a natural number, list, and trees, now we can define all of them with one side condition that I marked here. We need this A to enjoy this other property with respect to the paragraph. And this is not so nice news, because in fact this holds only for finite types. So in particular, we can have streams and trees only at finite types. But this is already something that can be useful in some of the applications I was mentioning before. This is what I have to present you today, and let me just conclude with something I hope you can take home. So the first thing I hope you will take home is that algebras and coalgebras encoding can make sense also in languages with limited complexity, and in particular with polynomial time complexity. It's an open question to check if they still hold also in classes lower than polynomial time. The other interesting observation is that the restrictive nature of this language forces us to have a more ugly encoding. So we need to tweak with this paragraph and bang everywhere the types. So this is the price we need to pay for it. And the third observation is that, like we saw for the case of the right distributivity, the underlying language still play a relevant role for expressivity, besides the fact that we have a notion of algebra and coalgebra. And this is, I think, something interesting to notice. And with this, I'm done, and I thank you for your attention.
So maybe this is really naive, but didn't your completeness result suggest that every sort of p-time Turing machine was expressible in the original calculus before you relaxed it?
Yes.
And didn't you show that everything in the relaxed calculus was in p-time?
Yes.
So doesn't this suggest that everything in your relaxed calculus could somehow be expressed in your original calculus?
Yeah, but yes. So
okay.
This is exactly the motivation. Sorry, did you finish with the question?
Yeah.
Okay. So this is exactly the motivation of our work. So we can encode everything that is polynomial via an encoding. But the problem is when we look at high-level programs, in particular we look at programs that have some interesting shape, like the one of algebra and coalgebra, we could potentially just go via the encoding. But in fact, we would like to give them directly to a programmer. So that's why we look for having some kind of restriction of this notion, but at the high level, without going through an encoding. You can think that is what we do every day. Nobody really go through the encoding via Turing machine when it has to prove the expressivity of the language.
Thanks very much. That was very good. So you've shown us that catamorphisms are related to p-time complexity.
Yeah.
And I'm wondering whether that result carries across to variations on catamorphisms, for example, mutual recursion. Yeah,
that's a very good question, and we didn't look into that. But I think, so this work say two things that I didn't put on this slide. That is, so we look at the encoding, but first we can now think also to add some operation that represent different kind of recursion and iteration using a type scheme similar to the one that we have found here. And I don't know if other encoding can work, but I'm confident that we can add other schema.
It's not that surprising that the paragraph does not commute with the construction that you use, in a sense that the bank commutes with the positive connectives, and the paragraph, it makes sense that it gets stuck. My question was, have you tried using negative products, for example, in the co-algebra case, and does it work? Is it easier to make it commute? So that would be.
So okay, we didn't try it. The reason why we took this approach is that it was it was a kind of open question for a while if this restriction of having paragraph not commuting for this language was something that we really needed. So there were people in the community that thought that this was a restriction needed. So our work also showed that this is not needed. What what it does, adding this distributivity, is that we break the proof, and that's fine, because we can recover it with a proof that is completely different. So it preserves soundness. So this is the reason why we target this approach.
Okay, thank you.
Okay, thanks again.
Thank you.